This video lesson is meant to cover the information found in Unit 0.3 on compounds. Recommended reading is the Rosengarten text, pages 12 through 14. In this section, we're going to be talking about compounds, and we are going to try to represent what compounds and actually elements look like as particle diagrams. We'll talk about what that means in a moment. So compounds, let's talk about the definition of a compound. A compound is when you have two or more different types of atoms chemically bonded. So they're connected through a chemical bond in a fixed proportion. Right, so for example, water. Water is H2O. What this means is that there are two hydrogens, and each one of those hydrogens is chemically bonded to an oxygen. All right, so that right there is a compound because we have at least two different types of atoms. Doesn't mean we have two atoms in total, because you can see here that there's three atoms. But two different types of atoms that are chemically bonded in a fixed proportion. Fixed proportion referring to the fact that it's always going to be two hydrogens to one oxygen in this compound. A compound can be broken down into its component elements by a chemical reaction. We're basically just saying the reverse of what we just said before, but you can take water and you can run electricity through it, and you can break these bonds, and as a result you will get two products. You will get hydrogen gas and you will get oxygen gas. So you can break down a compound, or a compound, it has the capability of having its bonds broken to get the individual elements separated. Now what we are looking at here is these are what we call particle diagrams, right? Because what we are looking at are the particles that represent what's called a binary compound and a ternary compound. So in this binary compound, binary means two, in this particular compound there are two types of atoms. And in this particular picture, like so this right here, right, has this type of atom where it's completely colored in, and it has this kind of atom. So binary, two types of atoms. Again, it doesn't mean that there has to be only two atoms, just two different types. Ternary compound means that there are three types of atoms. And if we look at one of these individual examples, we have an atom that we're showing as completely colored in. We're showing an atom that is not colored in, and we are showing an atom that is partially colored in. So I'm just going to shade that gently. Okay, so ternary compound is just a term to recognize that there are three different types of atoms. Now in this case, this is a compound that has only three atoms total in it, but that doesn't have to be the case. You're just looking for three types of atoms that are there. In either one of these cases, we collectively typically refer to this whole thing as a compound. You have a sample of this particular compound. This is a sample of this other compound. But one of these particles, right, in this sample there's 1, 2, 3, 4, 5, 6, 7 particles. Up here there's also 7 particles of that compound. That smallest particle, for example, right here, or up here, we generically refer to that smallest particle as a molecule. Okay, so when we are looking at a compound, the smallest particle of a compound is always going to be called a molecule. Comparing this to the smallest particle of an element, which was in the previous lesson, the smallest particle of an element can either be an atom. For example, if it's just this, that is an atom. But an element can also be a molecule. the smallest particle might also be a molecule. For example, when we have what's called a diatomic, okay, the diatomic elements. The diatomic elements, there are only 7, right? And we remember them with this acronym, Brinkelhoff. And what this means is the element bromine actually exists as a diatomic molecule of Br2. Iodine exists as a diatomic molecule that we call I2. N is nitrogen at N2, Cl, chlorine, Cl2, hydrogen, H2, oxygen, O2, and fluorine, F2. So each one of those 7 elements, the way they naturally exist in nature is diatomically. A bromine will find another bromine and they will be chemically bonded. And when that happens, we say that particle, because there's 2 atoms stuck together, we call that a molecule. Over here, an atom is the smallest particle of an element that is considered a monoatomic element. Most elements, when they exist naturally, exist as monoatomic elements, as single separate atoms. There are 7 elements that exist diatomically in nature. Okay, so smallest particle of a compound is always going to be a molecule because you have to have, remember, a compound, you have to have at least 2 or more different types of atoms chemically connected. So right there, the smallest particle has to be a molecule, it can't be a single atom. Okay, let's take a look at interpreting chemical formulas, subscripts, and coefficients. A chemical formula, for example, is something like H2O. That's a chemical formula for water. O2, that's the chemical formula for oxygen gas. C6H12O6, that's the chemical formula for glucose. Right? This is water, this is oxygen gas, this is glucose. There is something, Na3PO4, this is something called sodium phosphate. Sodium phosphate is often used as a gritty cleanser, but it's pretty caustic, so it's not something that is commonly used. So what's in a chemical formula? The first thing that's in there, and that I forgot to write in here, is the element symbol. Okay, so chemical formula has number 1, element symbols, right? The H for hydrogen, the O for oxygen, the C for carbon. So that's the first thing that has to be in a chemical formula. Oftentimes, there are subscripts. Subscripts are the little lower number. I'm going to say to, this is the word to the right of an element symbol. Right, so these little numbers here that are, so this 2 here is telling you how many hydrogen atoms are going to be in this chemical formula. Right, so that's what the subscript does, is it tells how many atoms of that element. Right, so in glucose, that means there are 6 carbons, 12 hydrogens, and 6 oxygens. Now, a coefficient, I'm not going to put this as number 3 because not all chemical formulas will have coefficients in front of them, but we do need to talk about them. Sometimes you're going to see a big number. Oh my goodness. Spelling is hard today. The big number that is to the left of a chemical formula. And what this does, for example, you might see something like 2 in front of the H2O. Okay, so that's an example of the coefficient. What this number does is it indicates how many particles you have. So when we say 2 H2Os, what we are saying is that we have, I'm going to try to squeeze this in here, if this is one H2O, right, that's one H2O molecule, you are also going to have a second one, like so. Okay, so when you have a 2 in front of the H2O, it's saying that you have 2 of those individual molecules of that compound. So let's try to apply this. That's what this next chart is going to do, recognizing that we have a key here. Hydrogens are going to be little open circles, oxygens are going to be colored in circles, nitrogens are squares, and carbons are triangles. So here, if we have H2O, right, this is our oxygen, these are our 2 hydrogens. First rule that we're going to talk about is the fact that there is no subscript after the oxygen. When you see that there is no subscript after the oxygen, this means there is only one of that atom. Right? And so what this is implying is that there's only one oxygen. You can see it here in the particle diagram. This right here is the oxygen. There is only one of them. And so ones are understood. You can put a 1 there, but it's unnecessary, and the absence of that 1 is going to imply that you have only one of those. The next example we're going to look at, our next rule that we need to keep in mind, is this number 2. Right? So when we have a subscript, in this case, of this, what this means, the subscript of 2 after the hydrogen, what does that mean? It means that we have 2 atoms of hydrogen. All right, so that's pretty evident. I think that's pretty straightforward. Here, what we have is the, what we're going to look at here is the coefficient. Okay, so in this case, we have a coefficient of a 7 before the chemical formula. Right? What that means is that we have 7 particles. In this case, those particles are molecules. Molecules because there's 2 different types of atoms stuck together in one of those particles. So there, but we'll call them 1, 2, 3, 4, 5, 6, 7 distinct particles of water. So the 7 is telling you how many of those particles are present. Lastly, in this next one, we see that we have parentheses. Okay, when we have parentheses around, in this case, the NH4, right, what you will do with that is you will distribute, which means to multiply, the subscripts that are inside. So the 4, that's a subscript that's inside the parentheses, times the subscript, let's keep that singular, subscript, outside the parentheses. So for example here, what this would mean is if we're taking this 2, first of all, there's a 1 next to the nitrogen, so we're going to multiply 2 times 1, and that means there's going to be 2 total nitrogens. If we're counting up hydrogens, 4 times 2, that's going to give us 8 hydrogens. Now, carbon and oxygen are not inside parentheses, so we don't have to distribute. We just have to recognize that there is 1 carbon and that there is 3 oxygens. So we can see this, how this is all stuck together, right? This whole thing is 1 molecule. All these atoms are stuck together. These are our hydrogens. We said that there are 8, and here's where they are located. 1, 2, 3, 4, 5, 6, 7, 8. There's 2 nitrogens. Nitrogens are represented by squares. So 2 nitrogens. There's 1 carbon. Carbons are represented as triangles, so there's 1 triangle. and there's 3 oxygens, 1, 2, 3. So the reason why this formula exists in this format is will be revealed when we start talking about ionic compounds and their formulas. And I just realized that perhaps that was all off screen. So I'll leave that right there for you to take a look at. The parentheses here around the NH4, we're going to distribute the subscripts inside the parentheses with the subscripts outside the parentheses. That's a multiplier. So 1 times 2 is 2. 4 times 2 is 8 for the hydrogens. Carbon and oxygen not in parentheses, so 1 carbon, 3 oxygens. And we see here that this works out. The nitrogens, which are squares, there's 2 of them. Hydrogens, which are open circles, there's 8 of them. Carbons, there's 1, represented by the triangle, and then the 3 oxygens are the colored in circles. All right, so let's take a look at counting atoms. All right, we won't have particle diagrams here, but let's take a look. Write the symbol of each element present in the compound, followed by the quantity of atoms of each element in the compound. So we're going to count up in this representation, how many sodium atoms are there? How many bromine atoms are there? Well, within the chemical formula, there's 1 of each. Like if I'm ignoring this coefficient for the moment, there's just 1 sodium and there's 1 bromine. But we have 12 of these particles. So we need to multiply or distribute the coefficients through. So 12 times 1 is going to give us 12 sodiums. 12 times 1 is going to give us 12 bromines. The next formula, ignoring the coefficient for a moment, I've got 3 elements. I've got aluminum, I've got oxygen, and I've got hydrogen. Again, ignoring the coefficient for the moment, we should recognize that in one of these molecules, I've got 1 aluminum, I've got 3 hydrogens and 3 oxygens. But we have 4 of these total molecules, so we have to, again, multiply by the coefficient. So for aluminum, 4 times 1 gives me 4. 1 times 3, right, we have 3 oxygens, times 4, because we have 4 molecules, we're going to have 12 oxygens. Hydrogens, we have 3 hydrogens in the molecule, but we have 4 molecules, so that's going to give us 12 hydrogens. Our next substance has gallium, Ga, chromium, Cr, and oxygen. So I guess we didn't need this last column at all. We have no coefficient. When there's no coefficient, that's just an implied 1. So that's going to make this process a little simpler. We don't have to worry about multiplying by a coefficient. So gallium, I see a subscript of 2 after the gallium. That means we have 2 galliums. Now we're looking at parentheses. So that means I have to take this outer subscript and multiply it by the inner subscript. So for chromium, I've got 3 times 2. That gives me 6 chromiums. Oxygen, 3 times 7 gives me 21 oxygens. Okay, so that's how you do an accounting. If you need to know how many atoms there are in a given formula, that's going to be a skill that you're going to want to make sure you're comfortable with, and for reasons that we are going to deal with later on. All right, let's go back to this idea of particle diagrams. We're going to focus on particle diagrams of pure substances. Okay, pure substances. An element is a pure substance. A compound is a pure substance. So let's, in turn, take a look at those. Let's get you all that in the picture there. Let's take a look at each one of those. Now, elements, as we saw, can be either monatomic, which are most elements, right? First of all, elements, you're going to recognize an element because there's only one type of atom. A compound, you are going to see 2 or more types of atoms. Okay, so that's going to be the quick way that you can tell that you're looking at either an element or a compound. A monoatomic element, there's not only one type of atom, but the atoms are existing monoatomically, meaning they are just existing as single independent atoms. Okay, so what we are looking at here, each one of these is a single atom, right? So let's just say here we have elements that exist as separate single atoms, and most elements exist this way, right? So just as examples, helium exists this way, iron exists this way, sodium exists this way. Helium, iron, sodium. Diatomic elements are the elements that exist as a bonded pair. Now, both of those elements in that bonded pair have to be the same element, right? There are only 7 elements that do this, and we just talked about them, but we're going to mention them here again, and we're going to remember that as Brinkel-Hoff, right? Br2, I2, N2, Cl2, H2, O2, F2. Not as one smushed together, that's just our acronym to help us remember that. Diatomic elements are going to be drawn as 2 atoms kind of touching like that. But those 2 atoms are clumped together, they are stuck together, and we're going to draw 3 particles. Oh, heck, let's draw 4 particles. Okay. So the difference here between elements and monoatomic elements and diatomic elements is the smallest particle, what we call the smallest particle. In monoatomic elements, these individual smallest particles are called atoms. In a diatomic element, these individual particles that exist separate from one another, they're not atoms, they are called molecules. Remembering that molecules are when you have 2 atoms stuck together in a bonded arrangement. Okay. In this case, they happen to be the same element, and that's okay, right? But the fact that there's 2 atoms stuck together chemically is why we will call that particle. There's four particles, 4 molecules in this sample. Up here we have 1, 2, 3, we have 6 individual atoms. Here we have 4 molecules, each molecule existing of 2 atoms. All right, let's take a look at compounds where we're going to have 2 or more different types of atoms in each substance. The difference here is binary versus ternary, right? So binary, if you recall, is where you have only 2 different elements bonded together. And it doesn't mean that there's only 2 atoms. Okay, so for example, one example is we could have something that looks like this, right? 2 different atoms stuck together. But another example is something that looks like this. Okay, 2 different types of atoms. It can be 2 total atoms, but it doesn't have to be. Okay. Either way, the smallest particle of this type of binary compound, we have to refer to each one of these particles as a molecule, right? Because a molecule is when you have 2 or more atoms stuck together, it doesn't matter what they are. But this particle we would refer to, this would be a molecule of a binary compound. This would be a molecule of a different binary compound. Ternary compounds have only 3 different elements bonded. But it doesn't mean only 3 atoms. Okay, so for example, and this is kind of a small box, but let's go with, we're going to go with an X in this circle, an X in this circle. We'll leave this one open, and then we'll draw another one like this. Okay, so 3 different types of symbols, even though there's 4 atoms stuck together here. That would be a ternary compound. Compound with an atom with X, atom that's open, and an atom that is colored in. Another example of a ternary compound might just only happen to have 3 atoms, and that's okay. So maybe something like this. Okay. The fact is there's 3 different elements that are bonded together. That's where the ternary comes from. And lastly here, each one of these individual particles, because these are compounds, any individual particle in a compound will be referred to as molecules. All right, so in this lesson, we looked at definitions of compounds. We talked about what kind of particles are in compounds. We showed how you can count atoms in compounds, and we tried to represent these compounds with particle diagrams. There should be a problem set for you to try. Go ahead and try that. Otherwise, I will see you back in the classroom.